In this video, we're going to look at writing ionic equations. Now, if you're doing Edexcel higher tier GCSE, there is always a question about writing ionic equations. So far, back in year 7, 8, we probably started with word equations, where we wrote a word equation, say for magnesium reacting with oxygen, it was magnesium plus oxygen makes magnesium oxide. And then we took that further by changing the words for symbols. So we did Mg plus O2 makes MgO. And then we balanced that. We did a balanced symbol equation, so that took that still further. Now with ionic equations, it's like a symbol equation, but we miss out ions that do not change their charge. And we miss out substances that don't change their physical state, i.e. whether they're a solid, liquid or gas or dissolved in water. Now you've done some ionic equations already. We did half equations in electrolysis, and these are examples of ionic equations because they have the charges on the ions that are involved, and they're turned into elements, and they have the electrons to balance out the charges. So we've got a few, this is just straightforward revision because you've done some ionic equations already. So these are ionic equations for electrolysis. So half equations in electrolysis are examples. Write a half equation for the cathode. The cathode, if you remember, is the negative electrode. So let's write a negative next to that. I always like to write the positive and negative next to the anode and the cathode. Simply because it just helps me picture what's going on and helps me get it right. Okay, so we've got write a half equation for the cathode anode when lead bromide is electrolyzed. Okay, so to remind you of lead bromide, that is made of lead ions, which are Pb2+, and bromide ions, which are Br-. Okay, so which of these is going to be attracted to the cathode, the negative electrode? Well, opposites attract, so the lead ion is going to be attracted there, and when it's in electrolysis takes ions and turns them back into their elements. So that's going to be Pb. So what we've got here is we've got a species that's changing its charge. So we're definitely going to include those in the ionic equation. The 2 plus Pb, the 2 plus lead is becoming Pb neutral. So that's changed its charge, so that definitely gets included in an ionic equation. And of course, to do that, it has to gain electrons. So there is our half equation, and that's an ionic equation. That's an example of an ionic equation. Likewise, the bromide ion in electrolysis in the lead bromide gets attracted to the anode. As soon as it touches that, it turns into the bromine molecule. So what we've got here is we've got something that was an ion, and it's bonded ionically in lead bromide, and as a result of this reaction, it's going to form bromine, which is of course covalent. And so that has no charge. So again, we've got the species changing its charge. So the bromide ion, how is it going to form the bromine? Well, it's got a negative charge here. So it's going to need to lose that negative charge. So it's going to need to give off electrons. So electrons are going to be produced. Before we do that though, let's balance this out. One bromide ion is not going to make 2 bromine atoms in that molecule. So we're going to need 2 bromide ions to make 2 bromine atoms in that molecule. And as I said a moment ago, they're going to give off electrons. Well, 1 bromide ion is going to give off 1 electron, so 2 bromide ions is going to give off 2 electrons. And there's a couple more here, so we can have I'll do this one, then you can have a go at that one on your own. So the cathode anode in water is electrolyzed. So water, to remind you, is about the only covalent substance we need to worry about that is going to form ions. So water is made of hydrogen ions and hydroxide ions. The cathode is negative, so it's going to attract the positive ion, the hydrogen ion. The hydrogen ion is going to be attracted to the electrode and turn into the hydrogen molecule. 1 hydrogen ion is not going to make 2 hydrogen atoms molecules, so we're going to need 2 hydrogen ions. So again, we've got the charged ion turning into a neutral molecule, so we've got change of, we call this the oxidation state, change on the charge on the ion. So that's why it goes into the ionic equation. How's it going to do that? It's going to have to gain electrons. Well, 1 hydrogen ion is going to gain 1 electron, 2 hydrogen ions are going to gain 2 electrons. The hydroxide ion touches the electrode and turns into oxygen and water molecules. So again, I've got a charged species here, and it's going to turn to 2 covalent substances. They are neutrally charged. So we need to balance this out. 1 oxygen, I've got 1 oxygen there, 2 oxygens there, 2 oxygens there, and 1 oxygen there, 3 oxygens. And I've got 1 hydrogen there and 2 hydrogens there. So I could, to balance this, put a 2 before that to balance the hydrogens, but that's never going to balance the oxygens. So let's go straight for, let's put a 2 there because 1 wasn't going to be enough. So 2 times 2 is 4 hydrogens. I'm going to put 4 hydrogens there. Now I've got 4 oxygens there, it was 2 there and 2 there. So that's now balanced in terms of atoms. And it's important to balance these in terms of atoms before we add electrons. The hydroxide ion is negatively charged. It's got too many negative charges. Well, electrons are negative, so it's got to lose those negatives. If it's losing the negatives are going to be produced. So they're going to be on the right-hand side, the product side of the equation. 1 hydroxide ion loses 1 electron. 4 hydroxide ions are going to lose 4 electrons. Okay, so that's just a revision of the half equations from electrolysis. And they are examples, let's say, of ionic equations. But we also need to be able to write ionic equations for full reactions. Now, I've come across lots of equations, lots of reactions so far in the course that we could write ionic equations for. So we have examples of this are neutralization and precipitation reactions, and we'll have a look at some of those in a moment. Before we do that, it's important to remember that atoms are not charged in covalent substances, but they are in ionic. Because we're looking at how the charges change, and if the charges change, then they go into an ionic equation. If the charges don't change, they don't go into an ionic equation. So we do need to know this. So how can we identify whether bonding is ionic or covalent? So quick reminder of year 10 again. For that we need a periodic table. So take an example here, lead bromide. How do we know if it's ionic or covalent? We need to get a periodic table out, and we need to draw on the periodic table the metal non-metal divide. And of course the metal non-metal divide goes down here. Metals are this side and non-metals are this side. Now, covalent bonding is non-metals only. So how can we identify whether bonding is ionic or covalent? Covalent bonding is non-metals only. An ionic bonding is a metal and a non-metal. So let's go back to that example of lead bromide we talked about. Lead bromide, well, lead is here, just there, Pb, and that therefore it's on this side of the metal non-metal boundary, so that's a metal. And bromine is here, and that's on this side of the metal non-metal boundary, so that's a metal and a non-metal. So that bonding has to be ionic. Okay, so that would be positive lead ions and negative bromide ions. Take a different example. Water, this is an example we used here, water. Well, hydrogen is up here, so that's on the non-metal side. Oxygen is here, non-metal side, so that's covalent. And that's important because we need to know charges, as I was saying. What else do we also need to know? We need to know the charges of these more complex anions. And I've just written them out here, so you've got them, because we need to know those as well if we're going to do ionic equations. Right, so next page is just to help you practice whether something's ionic or covalent. Magnesium oxide, for example, back to the periodic table, magnesium here, therefore on the metal side. Oxygen here on the non-metal side, so that one is ionic. Okay, and now if it is ionic, we need to know the charges. So magnesium is here in group 2. So everything in group 2 has got 2 electrons in its outer shell, so that's going to form the 2 positive ion. Everything in group 6 has got 6 electrons in its outer shell, so it needs 2 more to fill its outer shell, so everything in group 6 is going to form the 2 negative ion. Group 7, 1 negative, group 5, 3 negative, so the periodic table tells us the charges on the ions. Group 1, 1 positive, group 2, 2 positives, we've already said, group 3, 3 positive. Okay, so the periodic table helps us. So that's going to be Mg2 plus and O2 minus. Let's quickly do this one here, calcium nitrate. So the nitrate ion is non-metals, okay, made of nitrogen and oxygen. These are non-metals, but together in that complex ion, that is an ion, and that is shown here. So the nitrate ion is the NO3 minus ion. So that's and calcium is of course over this side here, and that's a metal. So we've got metal and non-metals. Okay, so the bonding here again is ionic. Now the nitrate ion, remember these complex ions, you can't find the charge in the periodic table, we just have to know those. That's going to be NO3 minus, and the calcium ion is in group 2 on the periodic table. So everything in group 2 has a 2 positive charge. It's got 2 electrons in the outer shell, so it's Ca2 positive. Okay. Let's quickly do this one here down the bottom here, carbon tetrachloride. Okay, what type of bonding is that? Well, carbon is here in the non-metal. Chlorine is here in the non-metal, so non-metal, that's covalent. Because it is covalent, there are no charges. These are elements. Elements are not charged. So where it says carbon and chlorine, charge if ionic, they're not charged because it's not ionic, it's covalent. Okay, so let's have a go and see if we can put some ionic equations together. So that's the base information we need. Now remember, for an ionic equation, okay, 4 ionic equations. Okay, let's just go back to this first paragraph because it's really important. We only show the ions that change their physical state, whether they're solid or dissolved, or their oxidation state, their charge. Okay, and we're going to ignore ions that keep the same charge and remain in solution, so we don't include those. So, for example, here, what have we got? We've got magnesium oxide. So is that ionic or covalent? Well, let's go to the periodic table. Magnesium, metal, oxygen, non-metal. So this is ionic, so that's Mg2 plus and O2 minus. So let's put the 2 plus and the 2 minus on there. Hydrochloric acid. This is made of hydrogen ions and chloride ions. And remember, with acids, okay, yes, that is covalent, but acids liberate hydrogen ions, so they do ionize. I know this is complicated and breaks some of our rules, but acids do ionize. Okay, here we've got the Mg magnesium chloride, so magnesium is a metal, 2 plus. Chlorine over here, group 7, single negative charge, so that's going to be 2 plus and minus. Okay, and water, this is now covalent, so this is not going to form charges at all. Right, so what has changed and what hasn't changed? The magnesium's gone from a solid to an aqueous, so that certainly is going to need to go there. That magnesium, likewise, the oxygen's gone from negative to neutral, so that's going to need to go in our ionic equation because both these have changed. They've changed either their state, the magnesium has changed from solid to aqueous, and the oxygen has changed its state as well. It's also changed its charge. That definitely goes there. Right, plus 2H plus. Okay, so the hydrogen ion here, is aqueous, so it's changed its state, so it's now liquid. And it's also changed its charge. It was positive, it's now liquid, so that's going to go in here. The chloride ion, that's aqueous, negative, that's aqueous, negative. So the chloride ion has not changed. So I'm going to write 2H plus the 2, because that's the stoichiometry number there, the balancing number. The hydrogen ion, because that's changed, and I've ignored the chloride ion because that has not changed. Okay, likewise over here now, the magnesium has changed. It was solid, and now it's aqueous, so that's going to go here. Okay, but we said the chlorine hasn't changed. So instead of writing magnesium like that, I'm going to put the charge on the ion there. Okay, so in an ionic equation, if we've got an ion without its partner, if you like, we need to put the charge on the ion there. And the water, we decided the water had all changed, so that's going to be H2O. And there is our ionic equation there. So it's a bit of practice. Okay, you have to put the charges on, but you can have a go at this. Quickly do this one. Copper oxide, as that's Cu2 plus. With the O2 minus ion, again ionic. Sulfuric acid, this is hydrogen ions, okay, because it's an acid, even though it appears covalent, because they're acids, they are ionic. Okay, the copper over here, that's Cu2 plus, and the sulfate ion, SO4 2 minus, that's the 2 minus ion on sulfate, and water is not charged because that's covalent. Right, copper, solid, copper aqueous, that goes in. Oxygen, solid. Oxygen's the liquid over here into the water, liquids, that goes in, so we can just simply write CuO. Hydrogen ions was positive and now neutral, so they're going to go in. Okay, the sulfate, SO4 2 minus aqueous, sulfate, SO4 2 minus aqueous, right, we're not including that. Now there's 2 hydrogen ions here, okay, so we now need to write that with a big 2 beforehand because these hydrogen ions are on their own and we need to put the H plus in. Okay, so the copper sulfate, the sulfate we're not including, we've said that. So that's simply going to be Cu2 plus because we've put the charge on the copper ion in, and we're going to put the water in as well. Okay, let's have a go at these ones down here. I'll leave that one, the one you can have a go at that on your own. This one down here now, lithium hydroxide. So lithium's a positive ion because one positive ion because it's in group 1 of the periodic table. There's lithium, so it's group 1, so it's 1 positive. The hydroxide ion, that's OH minus. That's OH minus for the hydroxide ion, and that was on our table here. Okay, the hydroxide ion, we just need to learn that, OH minus. The hydrogen ions here are, this is nitric acid, so that's H plus, and the nitrate ion is NO3 minus. This is Li plus and NO3 minus, and this is water, so it's not charged. Okay, so lithium is a positive aqueous ion. The lithium here is a positive aqueous ion. We're not going to include that. The hydroxide ion is aqueous, but then is going to form this water. That's liquid, so we are going to include that because we're going from aqueous to liquid. Likewise, the hydrogen ion here was aqueous and it's going to form this water molecule, so that's going to be liquid, so we're going to include that. But the nitrate ion, NO3 minus aqueous, makes the nitrogen ion NO3 minus aqueous. So simply we need the hydroxide ion plus the hydrogen ion makes water. And we don't include anything else. And it looks like there's not enough there. But every other ion maintains its charge and its state. So we don't include them. Okay, I'll leave you to have a go at those. A couple more to have a go there. Lots and lots to have a go at on these things. I'll miss the whole next page. You can have a go at those. And we'll do them in lessons as well, obviously. Precipitate reactions. Let's do this one. Silver nitrates. Ag plus, okay, I'm just going to tell you that one. You can't look at that on the periodic table. I'll tell you that in lessons. And nitrate, NO3 minus. Sodium is group 1, so it's 1 plus. Chlorine is group 7, so it's NaCl negative. Sodium, Na plus, nitrate, NO3 minus. Ag plus, Cl minus. That's all our charges. These are all ionic. These are all ionic. Okay, now we've got Ag plus is aqueous. Ag plus is solid, so that's definitely going to go in. Nitrate, NO3 minus aqueous, NO3 minus aqueous, that doesn't go in because neither the charge nor the state change, so let's put the charge on the silver ion, now we know it's on its own there. Plus, okay, sodium, Na plus there, we're not including that, are we? Because that's the same charge and it's the same state. Cl minus aqueous, Cl minus solid. Right, so we're going to include that because that's changed its state. So Cl minus, and then arrow, AgCl. Okay, and that's that ionic equation there because that is solid and these were aqueous to start with. And you have a go at those ones. Okay, I shall leave that video there because that's more than long enough and it hopefully gives you an idea of how to write ionic equations. If you are looking at this without this workbook and you think the workbook's useful, they're all found on elshamhighchemistry.com. They're free to download and share. Please acknowledge AHS if you're doing that, and that's absolutely fine. Thank you.